Tonight, we are going to drift toward one of the strangest surprises the James Webb Space Telescope has found so far. Not a giant planet, not a nearby moon, not a familiar nebula glowing gently in our own galaxy. Tonight, we are going far deeper, almost all the way back to the first chapters of cosmic history, to a time when the universe was young, dark, and still learning how to build galaxies. And there, in Webb's infrared images, astronomers found something quietly unsettling. Tiny red points of light, compact and faint, but too bright, too common, and too strange to ignore. They have a simple nickname, little red dots. It almost sounds sweet, like something soft and harmless. But the name hides the mystery. These objects are not nearby red stars. They are not ordinary galaxies like the Milky Way. They are distant sources from the early universe, so far away that their light has been stretched by cosmic expansion until it falls into the infrared glow that Webb was designed to see. Some of them existed when the universe was only a few 100 million years old. And somehow, inside these tiny red points, there may be rapidly growing black holes, dense gas cocoons, intense starbursts, or some combination we still do not fully understand. When astronomers first began seeing them in Webb's earliest deep surveys, the reaction was not exactly panic. Science does not usually work that way. But there was a feeling of genuine surprise. Hubble had looked deep into the universe for decades, and it had given us beautiful images of early galaxies, scattered like embers in the darkness. But Webb opened a new infrared window, and behind that window were more red compact objects than expected. They appeared small on the sky, almost star-like, but their distances placed them in the young universe. They were not just strange because they were far away. They were strange because they seemed to represent a population that had been hidden from us until Webb could finally see it. To understand why this matters, imagine looking into a quiet, dark room with a dim flashlight. For years, you see the obvious shapes, large furniture, a doorway, a few objects on a table. Then someone hands you a new light, tuned to a color your eyes could not see before. Suddenly, small glowing things appear everywhere, not because they just arrived, but because you were not using the right light to notice them. That is what Webb did for the early universe. It did not create the little red dots. It revealed them. They had been there all along, waiting in ancient light, carrying information from a time when the first galaxies and black holes were growing faster than many models expected. The phrase early universe can feel abstract, so let us slow it down. The universe is about 13.8 billion years old. The Earth is about 4.5 billion years old. The Sun is also about 4.6 billion years old. Human history, even generously defined, is almost nothing compared with those numbers. But the little red dots take us to a time long before Earth, long before the Sun, long before the Milky Way looked the way it does now. Some of these objects appear from an era less than 1.5 billion years after the Big Bang, and some confirmed black hole examples reach back to only about 500 million years after the beginning. 500 million years after the Big Bang may sound like a long time, but cosmically it is incredibly early. If the universe's entire history were compressed into one calendar year, then 500 million years would fall in mid-January. The galaxies, stars, and black holes we see today would still be far in the future. Heavy elements would still be rare. The first generations of stars would only recently have begun enriching space with carbon, oxygen, and dust. Yet Webb is showing us that by this early time, compact systems had already become complicated. Some may already have contained massive black holes wrapped in thick clouds of gas. That is the quiet tension at the center of tonight's journey. The universe was young, but some of its structures already looked surprisingly mature. Not mature in the sense of calm and settled like the spiral galaxies we see today, but mature in the sense that complex processes had already begun. Gas had collapsed, stars had formed, some stars had died, black holes may have begun feeding, dust may have appeared. The raw simplicity expected at cosmic dawn was already giving way to complexity, heat, gravity, radiation, and growth. Webb was built for this kind of question. Its golden mirror, made of 18 hexagonal segments, gathers faint infrared light from the deepest observable universe. Infrared light is essential because the farther away a galaxy is, the more the expansion of space stretches its light. Ultraviolet and visible light emitted by early stars does not arrive to us as ultraviolet or visible light anymore. It arrives stretched, softened, and reddened into the infrared. Webb is not simply looking far away. It is looking at ancient light translated by the expansion of the universe. This is why the little red dots matter for both science and imagination. They are tiny in our images, yet they represent enormous questions. How did the first supermassive black holes begin? Did they grow from the collapsed remains of the first stars, slowly feeding over time? Or did some begin as much heavier seeds, formed directly from huge clouds of primordial gas? Did black holes form before their host galaxies were fully assembled? Did they help shape those galaxies from the inside out? And why do so many of these compact red objects seem to appear during a particular window of cosmic time and then fade from view later? Tonight, we will move gently through those questions. We will begin with Webb's view into cosmic dawn. Then we will explore how redshift turns distance into time, how astronomers separate a normal galaxy from a black hole in disguise, and why the little red dots have become one of the most fascinating puzzles of modern astronomy. We will visit Kuiper's LRD-Z9, one of the most distant confirmed black holes yet found, present when the universe was only about 3% of its current age. And we will step back to ask what these objects reveal about the first galaxies, the first black holes, and the astonishing speed at which the universe learned to become complex. You do not need to hold every number in your mind. Let the details pass gently, like faint starlight crossing a quiet sky. The important feeling is scale. A tiny red point in a telescope image can contain billions of years of history. A small smudge can be a doorway into the earliest black holes. A soft infrared glow can tell us that the universe, even near the beginning, was already more active, more creative, and more mysterious than we imagined. To make sense of these little red dots, we first need to understand how Webb sees the past. In everyday life, light feels immediate. You turn on a lamp and the room is lit. You look across a street and you see what is there now, or so it seems. But light always takes time to travel. Light from the moon takes a little over a second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest stars takes years, and light from the galaxies Webb studies can take more than 13 billion years to arrive. This means a telescope is not only a device for seeing distant places, it is a device for seeing distant times. The farther away an object is, the older the light is when it reaches us. When Webb sees a galaxy that existed 500 million years after the Big Bang, it is not seeing that galaxy as it is now. It is seeing that galaxy as it was when the universe was still very young. The galaxy may no longer exist in that form. It may have merged with others, grown larger, faded, or changed beyond recognition. But its ancient light continues traveling, carrying a message from its beginning to ours. The challenge is that this ancient light has been changed by the journey. The universe is expanding, and as space itself expands, light traveling through that space gets stretched. Short wavelengths become longer wavelengths. Blue light shifts toward red. Ultraviolet light shifts into visible and infrared. This stretching is called cosmological redshift. The larger the redshift, the farther back in time we are looking. It is not a perfect intuitive measure, but it is one of the most important tools astronomers have for turning light into a cosmic timeline. For a nearby galaxy, redshift might be small. For a galaxy near cosmic dawn, redshift can be enormous. The record-breaking galaxy JADES-GS-z14-0, for example, has been observed at a redshift of about 14, meaning its light comes from less than 300 million years after the Big Bang. That is so early that astronomers are effectively watching the universe build some of its first luminous structures. Webb does not see these galaxies because they are nearby or bright in the ordinary sense. It sees them because its infrared instruments are sensitive enough to catch light stretched almost beyond recognition. One important signature astronomers use is called the Lyman break. In very early galaxies, ultraviolet light from young stars gets absorbed by neutral hydrogen gas. Below a certain wavelength, the light drops away sharply. As the universe expands, this break shifts to longer wavelengths. By finding where the break appears in a galaxy's spectrum, astronomers can estimate how much the light has been stretched, and therefore how long it has been traveling. This is one of the ways Webb confirms that certain galaxies really are among the earliest known objects, rather than nearer imposters that only look red. A spectrum is one of astronomy's most powerful tools. An image shows where light is. A spectrum shows what that light is made of. It spreads light into wavelengths, like a more precise version of a rainbow, and reveals the fingerprints of elements, molecules, hot gas, dust, and motion. Hydrogen leaves certain emission lines. Oxygen leaves others. Fast-moving gas around a black hole can broaden those lines, smearing them across wavelengths because some gas is racing toward us and some is racing away. In the little red dots, those spectral fingerprints are often the key to deciding what kind of object we are seeing. Webb's NIR-CAM, its near-infrared camera, can find the tiny red sources in deep images. Webb's NIR-SPEC, its near-infrared spectrograph, can take their light apart and measure redshifts, emission lines, and clues to their physical nature. Webb's MIRI, its mid-infrared instrument, can look even farther into the long wavelength glow where warm dust, hidden black holes, and older stars may reveal themselves. Together, these instruments let astronomers move from "there is a strange red point" to "there may be a rapidly accreting black hole hidden inside this object." Wow! But even Webb cannot answer everything at once. These objects are incredibly distant, and they are tiny on the sky. A little red dot may represent a compact galaxy, a black hole surrounded by dense gas, a starburst wrapped in dust, or a combination of several processes. The light is faint. The signals are subtle. Different models can sometimes explain the same data in different ways. That is why the little red dot mystery is not solved by a single image. It takes many objects, many spectra, and careful comparison with simulations to understand what population we are really seeing. Before Webb, astronomers already knew the early universe must have formed the first stars and galaxies. They had models for how dark matter gathered into halos, how gas fell into those halos, cooled and formed stars, and how the first galaxies merged into larger systems. They also knew that supermassive black holes existed surprisingly early, because distant quasars had been observed less than 1 billion years after the Big Bang. But Webb has widened the view. Instead of only finding rare, extremely bright quasars, it is revealing smaller, fainter, more numerous objects that may represent a hidden growth phase. This matters because rare bright quasars are like seeing only the tallest flames in a vast forest. They tell you fire exists, but not how the forest first caught. Little red dots may be closer to the kindling. They might show an earlier, dustier, more crowded stage when black holes are still wrapped in gas, galaxies are still compact, and light has not yet escaped freely. If that is true, they could help connect the earliest black hole seeds to the enormous quasars we see later in cosmic history. And all of this is happening inside a universe that was changing rapidly. In the first few 100 million years, much of space was filled with neutral hydrogen. As the first stars and galaxies turned on, their ultraviolet light gradually ionized that hydrogen, transforming the universe from a foggy, neutral state into the transparent cosmos we observe today. This era is called rionization. Little red dots appear during and after this period, when the first luminous structures were not only forming, but actively changing the space around them. So when we talk about Webb finding something that seemed almost impossible, we should be careful. It does not mean physics is broken. It does not mean the Big Bang model has collapsed. It means the early universe may have been more efficient, more crowded with rapid growth, or more complicated than some models assumed. The most exciting discoveries usually live in that space between expectation and observation. Webb is not simply giving us answers. It is showing us where our questions need to become better. Now let us come closer to the little red dots themselves. In Webb images, they can look almost underwhelming, a small red spot against black space, sometimes a soft core surrounded by a faint red haze. Nothing like the dramatic spiral arms of nearby galaxies, or the glowing clouds of a nebula, or the sweeping rings of Saturn. And yet these tiny dots are important precisely because they are compact, distant, and strange. Their simplicity in the image hides complexity in the spectrum. Large samples suggest that these objects become common around roughly 600 million years after the Big Bang, and then decline in number by around 1.5 billion years after the Big Bang. That timing is one of the first clues. They do not seem to be a normal class of galaxies that persists in the same form throughout cosmic history. They look more like a phase, something that happens in the early universe, lasts for a while, and then changes or disappears as galaxies grow. Black holes clear their surroundings, or dust and gas are rearranged. One possible explanation is that little red dots are compact galaxies undergoing intense star formation. In this picture, their light comes mostly from stars, but the stars are packed into unusually small regions. The red color might come from dust. Dust grains absorb short wavelength light and re-emit energy at longer wavelengths, making a galaxy appear redder. If these objects are star-forming galaxies, then they may represent some of the densest stellar environments ever observed. Imagine the early universe squeezing star formation into tiny knots of gas, where huge numbers of stars are born in a space much smaller than a modern galaxy. But that explanation has difficulties. Some little red dots appear too compact, too bright, or too unusual in their spectra to be explained by stars alone. The amount of stellar mass required can be hard to assemble so early. The shapes of their light distributions can look more like point sources than extended galaxies, and in some cases, spectra show signs of fast-moving gas, the kind of motion astronomers associate with material orbiting close to a black hole. That pushes us toward a second possibility. Many little red dots may contain active galactic nuclei, or AGN. An active galactic nucleus is powered by a black hole feeding on gas. The black hole itself emits no light from inside the event horizon, but the gas falling toward it heats up, compresses, accelerates, and shines. Around a feeding black hole, matter can move at thousands of kilometers per second. When that gas emits light, the motion broadens the spectral lines. So a broad hydrogen line can act like a clue, telling astronomers that somewhere in the center of the object, gas is moving in the deep gravitational well of a black hole. If many little red dots are AGN, then they may be a missing stage in black hole growth. The early black hole is there, but it is not yet a brilliant exposed quasar. It may be buried in thick gas. It may be surrounded by dust. Its light may be reddened as it escapes. From far away, Webb sees a compact red source. Inside, the object may be a young black hole growing rapidly, wrapped in a dense cocoon. That would help explain both the red color and the unexpected brightness without requiring an impossible number of stars. This idea has a gentle but unsettling implication. In the early universe, black holes may not have been rare endpoints of galaxy formation. They may have been central actors from the beginning. We often imagine galaxies forming first, then their black holes growing later at the center. But little red dots suggest that in some systems, black holes may have grown very early, perhaps even outpacing the stars around them. The black hole may not simply be a quiet resident inside the galaxy. It may be a young engine shaping the galaxy as the galaxy itself is still being built. There are also hybrid explanations. A little red dot could contain both a compact star-forming galaxy and a buried black hole. In fact, that may be the most natural picture for many of them. Galaxies are messy. Gas falls inward. Stars form. Black holes feed. Dust absorbs and re-emits light. Winds push material away. Radiation changes the chemistry and ionization state of the gas. A simple label like galaxy or black hole may not capture the reality. These objects may be small, but they may be physically crowded, with many processes happening at once. Another idea that has gained attention is the so-called black hole star picture. This does not mean a normal star with a black hole inside in the familiar science fiction sense. It refers to a dense gas object powered by accretion onto a black hole, where the surrounding gas glows in a way that can mimic some features of starlight. In such a model, the black hole is deeply embedded, and the light we see comes from the envelope around it. This is still an active and debated area, but it shows how creative astronomers have had to become to explain the data. Part of the mystery is that many little red dots do not behave exactly like ordinary quasars. Classic active black holes often emit strong X-rays. Some little red dots appear faint in X-rays or difficult to detect at those wavelengths, which complicates the AGN interpretation. If a black hole is buried behind dense gas, X-rays may be absorbed, or the black hole may be in a growth phase that does not look like a nearby quasar, or there may be multiple populations mixed together. The quietness in X-rays is not a simple answer. It is another clue. This is why astronomers collect samples. One object can be misleading. 100 objects reveal patterns. When researchers search across surveys like SEERS, JADES, NG-Deep, rubies and capers, they are not just collecting dots. They are building a population. They ask how many there are at each redshift, how their colors change, how often they show broad emission lines, whether they are detected in X-rays, whether they are compact in shape, whether their light suggests dust, stars, gas, or black holes. Slowly, the population begins to speak. The picture that is emerging is not finished. Many little red dots likely involve accreting black holes, but not every object may be the same. Some may be compact starbursts, some may be buried AGN, some may be transitional objects that later become more ordinary galaxies or quasars. That uncertainty is part of what makes them fascinating. They are not a solved category. They are an active frontier. Webb did not simply confirm something astronomers already expected. It gave us a new puzzle written in red infrared light from a time when the universe was just beginning to assemble itself. One of the most powerful examples of this mystery is an object called Capers LRD-Z9. Its name is not poetic, but it is precise. Capers refers to the Candles Area Prism Epoch of Rayonization Survey, a Webb program designed to study extremely distant galaxies. LRD means little red dot, and Z9 tells us we are dealing with a very high redshift, a source from the early universe. Capers LRD-Z9 is not just another distant red smudge. Spectroscopy has confirmed it as a broad-line active galactic nucleus at a redshift of 9.288. Meaning we see it roughly 500 million years after the Big Bang. That number should feel startling. 500 million years after the Big Bang is almost as far back as current technology can practically confirm this kind of black hole signature. The universe at that time was young, not empty, but still under construction. Galaxies were smaller. Heavy elements were less common. Dust production was still developing. Yet Capers LRD-Z9 appears to contain a growing supermassive black hole, one massive enough to force astronomers to think carefully about how such objects form so quickly. The key evidence comes from Webb's spectrum. In that spectrum, astronomers saw a broad hydrogen beta emission line, a sign of gas moving at high speed near a black hole. The line is broad because the gas is not sitting still. Some of it is moving toward us, some away from us, all of it caught in the intense gravity of the central engine. This is the kind of signature that separates a real accreting black hole from a galaxy that is merely red or bright. It is the difference between seeing a strange glow and seeing the fingerprint of the engine that makes the glow. The black hole mass estimate is not a single simple number. Astronomers often give a preferred or canonical value and then a wider range that accounts for systematic uncertainty. For Kuiper's LRDZ9, the canonical estimate is tens of millions of solar masses, while wider uncertainties allow values that could reach hundreds of millions. Either way, the object is remarkable because it appears so early. A black hole that massive at that time has not had much cosmic history in which to grow. The question becomes, how did it get so big so fast? To grow a black hole, you need mass to fall in. That sounds simple, but there are limits. As gas falls toward a black hole, it heats up and emits radiation. That radiation pushes outward on the surrounding gas. If the black hole feeds too aggressively, its own light can blow material away, slowing growth. The balance between gravity pulling in and radiation pushing out is related to what astronomers call the Eddington limit. A black hole can exceed this limit in certain conditions, but sustained growth still requires a supply of gas and a way for that gas to lose angular momentum and reach the center. If the earliest black holes began as the collapsed remnants of the first massive stars, their seeds may have been only tens or hundreds of solar masses, perhaps more in unusual cases. Growing from that size to tens of millions or hundreds of millions of solar masses in only a few 100 million years is difficult unless the black hole feeds almost continuously, very efficiently, or sometimes above the usual limit. That is possible, but demanding. It is like asking a child to become a giant before the first morning is over. Another possibility is that some black holes began with much larger seeds. In the direct collapse scenario, a huge primordial gas cloud avoids fragmenting into many stars and instead collapses into a massive black hole seed, perhaps thousands to hundreds of thousands of solar masses from the start. That gives the black hole a head start. It does not need to grow from a tiny stellar remnant. It begins already large, and then feeding can make it enormous. Little red dots may help test whether such massive seeds were common or whether other pathways are needed. There are more exotic possibilities too, including primordial black holes formed in the very early universe, or unusual interactions involving dark matter and gas. These ideas remain speculative, and not every model is equally supported. But the important point is that Webb has moved this question from theory into observation. We are no longer only asking whether early black holes could exist. We are seeing candidates and confirmed objects that force the question into sharper focus. The universe is giving us examples, and our models have to explain them. Kuiper's LRDZ9 also tells us something about the red color of little red dots. The light may be passing through a thick cloud of gas around the black hole, shifting and reshaping the spectrum. The object may be gas enshrouded, with dense material surrounding the active nucleus. This would make sense of a black hole that shines brightly while still looking red and compact. It is not a clean exposed quasar blazing unobstructed into space. It is more like a young engine hidden behind a veil, bright enough to be seen, but not yet fully revealed. This hidden phase is important because the brightest quasars in the later early universe already contain black holes with masses of billions of suns. Those quasars are spectacular, but by the time we see them, much of the growth has already happened. Little red dots may show an earlier stage, when black holes are smaller, more buried, and more common. They could be the bridge between the first seeds and the giant quasars that appear later. If so, each little red dot is not just an odd object. It is a clue to how the cosmic monsters were born. There is also a deep relationship between black holes and galaxies. In the modern universe, large galaxies almost always contain central supermassive black holes, and the mass of the black hole often correlates with properties of the host galaxy. This suggests some kind of co-evolution. Galaxies feed black holes, Black holes heat and blow gas, and together they regulate growth over billions of years. But in the early universe, Kuiper's LRDZ9 and similar objects hint that the relationship may begin in a more uneven way. The black hole may be unexpectedly large compared with the stars around it. That is why astronomers sometimes describe these early black holes as overmassive, not necessarily because they are the most massive black holes ever seen, but because they seem heavy relative to their young host galaxies. In today's universe, a black hole usually makes up a small fraction of the stellar mass of a galaxy's central bulge, in some little red dots. The inferred black hole fraction may be much larger. It is as if the central engine grew before the surrounding city was fully built. That image may not be perfect, but it captures the tension. The calm wonder of this discovery is that it does not make the universe less understandable. It makes it richer. A simple timeline would say, first stars, then galaxies, then black holes grow slowly. Webb is showing something more interwoven. Stars, gas, black holes, dust, and radiation may all be emerging together, shaping each other from the beginning. Kuiper's LRDZ9 is a small red point in a telescope image, but it opens a door onto one of the oldest questions in cosmic history. How did darkness learn to build engines of light? The little red dots are only one part of Webb's early universe surprise. Another part comes from the galaxies themselves. Webb has found galaxies at redshifts so high that we are looking back to the first few 100 million years after the Big Bang. One of the most famous is JADES-GS-z14-0, observed as it was less than 300 million years after the universe began. More recently, Webb has pushed to candidates and observations even closer to the beginning, such as MoM-z14, reported as appearing around 280 million years after the Big Bang. These discoveries are not exactly the same as little red dots, but they belong to the same larger story. Webb is finding luminous structures extremely early. Some of them are brighter, larger, or more chemically developed than expected. This does not mean the universe is impossible. It means the first galaxies may have formed stars efficiently, perhaps in intense bursts, and that our earlier expectations may have underestimated how quickly small systems could shine. Webb is not merely filling in a known picture. It is redrawing the first page with finer ink. To understand the surprise, consider what must happen before a bright early galaxy can exist. First, matter has to gather into dark matter halos. Gas has to fall into those halos. The gas has to cool. Stars have to form. Massive stars have to shine. Some massive stars must die quickly, producing heavier elements like oxygen and carbon. Those elements can then appear in later gas and stars. All of this takes time. In the modern universe, these processes can unfold over millions and billions of years. But at cosmic dawn, Webb is seeing evidence that some of it happened very quickly. JADES-GS-z14-0 is especially striking because it is not only distant, it is bright. Webb's observations indicate that this galaxy was already producing a large amount of light at a time when the universe was less than 3% of its current age. That brightness may come from vigorous star formation, perhaps with stars forming in ways that differ from those in later galaxies. It may also involve nebular emission, where gas around young stars glows strongly. The exact details are still being refined, but the basic message is clear. The young universe was capable of luminous galaxies earlier than many expected. The detection of elements in such distant systems is another clue. Heavy elements are not made in the Big Bang in large amounts. The early universe began mostly with hydrogen, helium, and a little lithium. Elements like oxygen, carbon, nitrogen, silicon, and iron are forged in stars and spread by stellar winds and supernova explosions. So if an early galaxy shows signs of oxygen or other heavier elements, it means stars had already lived and died before the light we are seeing was emitted. Cosmic history had already begun cycling material through stars. That idea is gentle but profound. When Webb sees an early galaxy with enriched gas, It is not seeing the very first moment of structure. It is seeing a young system that already has a past. Even at 280 or 290 million years after the Big Bang, there may have been earlier generations of massive stars that formed, burned brightly, exploded, and seeded the next generation. The first galaxies were not static objects. They were active ecosystems of gas, gravity, light, and death. This helps explain why early galaxies can be more luminous than expected without requiring impossible physics. Massive stars are extremely bright and short-lived. A compact galaxy undergoing a sudden burst of star formation can shine strongly for a brief period. Nebula gas around those stars can add emission lines that boost brightness in certain Webb filters. Dust can redden the light. Black holes can contribute. The result can be a galaxy that looks surprisingly bright or red in a telescope image, but becomes understandable once all the ingredients are carefully modeled. Still, the models are under pressure. Before Webb, many predictions were based on what Hubble could see, plus simulations calibrated to known galaxies. Hubble was a magnificent telescope, but it could not see the infrared universe with Webb's depth and sensitivity. Webb revealed objects that Hubble missed or could not characterize. That means some pre-Webb models were built with incomplete observational guidance. When new data arrives, models must adapt. That is not a failure of science. It is the normal rhythm of discovery. There are several ways models may need adjustment. Star formation in early galaxies may have been more efficient than assumed, meaning gas turned into stars quickly. The first stars may have had different masses, perhaps with more massive stars that shine brighter. Bursty star formation may make galaxies flicker in brightness, so Webb catches some during luminous phases. Feedback from supernovae and black holes may behave differently in small young systems. Dust may appear earlier or in different distributions. Each possibility changes how we interpret the light. The little red dots add another layer because some of the compact red light may not be stellar at all. If black holes are contributing substantially to the brightness, then early galaxy masses inferred from starlight alone may be overestimated in some cases. A source that first appears to be a very massive ancient galaxy could partly be an active black hole wrapped in gas. This has happened before in astronomy. A new class of objects appears to challenge everything, and then better spectra reveal that multiple components are blended together. The challenge becomes more subtle, but not less interesting. The phrase "too early" is useful for thumbnails, but in the script we can soften it into the real scientific question. Not these objects cannot exist, but what growth pathway made them possible? Did black holes start heavier? Did they feed faster? Did galaxies form stars in compact, intense bursts? Did dust and gas mimic older stellar populations? Did early cosmic environments allow structures to assemble more quickly? These are the questions Webb is helping astronomers ask with more precision. The beauty of cosmic dawn is that every observation is a time capsule. A small source at redshift 14 is not just far away. It is a message from the time before the universe became familiar. A little red dot at redshift 7 or 9 is not just red. It is a clue to a phase of black hole and galaxy growth that may have been common, brief, and hidden from previous telescopes. We are watching the universe practice. We are seeing it make stars, enrich gas, build black holes, and assemble galaxies when the cosmic story was still young. And in that sense, the early universe is not only a mystery, it is a nursery. It is not quiet, even if the images look still. It is full of collapse, ignition, radiation, and transformation. Webb's strange red dots and record-breaking galaxies remind us that the first chapters were not simple. They were dense with possibility. Out of the early darkness came the first islands of light, and some of those islands were already harboring engines powerful enough to shape everything that came after. So what do the little red dots mean? The honest answer is that astronomers are still working it out. That is not a weakness. It is the reason they are exciting. Science is most alive when the data is clear enough to demand attention. but not yet simple enough to fit neatly into a textbook. Webb has shown us a population of compact red objects in the early universe. Some show signs of accreting black holes. Some may be dense star-forming galaxies. Some may be buried engines wrapped in gas. Together, they point to a young cosmos that grew more quickly and more intricately than we expected. The next step is not a single dramatic announcement. It is patient work, more spectra, deeper imaging, X-ray observations from telescopes like Chandra, sub-millimeter observations from ALMA, which can trace dust and cold gas, mid-infrared data from Webb's MIRI, which can reveal hidden heat from buried black holes, statistical studies that compare hundreds of objects, simulations that test how gas, stars, black holes, dust, and radiation interact in the first billion years. The mystery will not be solved by one image. It will be softened, clarified, and shaped by many lines of evidence. This is one of the reasons the story is perfect for gentle science. There is no need to rush to an answer. We can let the uncertainty breathe. We can imagine astronomers looking at a small red source in a deep field and realizing that it may contain a black hole older than almost anything we have ever confirmed. We can imagine photons leaving that source when the universe was still young, crossing expanding space for more than 13 billion years, and finally landing on a golden mirror in the quiet darkness beyond the moon. That journey is already astonishing, even before we decode the data. The little red dots may also change how we think about supermassive black holes today. Nearly every large galaxy in the modern universe seems to host one. The Milky Way has Sagittarius A at its center, a black hole about 4 million times the mass of the Sun. Other galaxies contain black holes of millions, billions, even tens of billions of solar masses. For a long time, one of the great questions has been how these black holes began. Were they born small and patient, or large and hungry? Webb is giving us a way to watch their possible childhood. If early black holes began as massive seeds, it could explain how quasars became enormous so soon. If they grew through super Eddington feeding, it would tell us that black holes can sometimes bypass the usual limits under special conditions. If little red dots are dense cocoons around young black holes, then the early universe may have hidden many growing engines behind gas and dust. And if some little red dots are mostly compact starbursts, then they teach us that early galaxies could pack extraordinary star formation into small spaces. Every possibility is valuable. These objects also remind us that seeing is not simple. A galaxy is not just what it looks like in one color of light. In ultraviolet, it may appear young and star-forming. In visible light, it may be faint. In infrared, it may glow red and compact. In X-rays, it may be quiet or active. In radio or sub-millimeter wavelengths, it may reveal gas, dust, or hidden energy. Astronomy is like listening to an orchestra, one instrument at a time. Webb has given us a new section of the orchestra, and suddenly we hear notes that were missing before. Future observatories will deepen the song. The Nancy Grace Roman Space Telescope will survey huge areas of the infrared sky, finding rare, distant objects across a much wider field than Webb can cover. Euclid is mapping dark matter and dark energy through billions of galaxies. ALMA can trace cold gas and early chemical enrichment. Ground-based extremely large telescopes will eventually measure faint spectra in more detail. Webb opened the door, but the next decades will bring more instruments, more surveys, and more chances to understand what these red dots really are. It is possible that in 20 years, the little red dots will feel less mysterious. They may have a clear classification, a place in the story of galaxy evolution, and a well-understood physical model. Students may learn about them as a normal stage of early black hole growth, or perhaps they will remain partly strange, with different subtypes and exceptions. Either way, this moment will be remembered as one of Webb's early gifts. It showed us that the universe still had surprises waiting in the first billion years. There is something calming in that. The universe is not finished revealing itself. Even after centuries of astronomy, even after Hubble, even after the cosmic microwave background, even after gravitational waves and exoplanets and black hole images, a new telescope can still look into a quiet patch of sky and find a class of objects that makes astronomers pause. The cosmos is not exhausted. It is not empty of wonder. It is old, vast, and still capable of surprising us with small red dots from the dawn of time. And perhaps the deepest meaning is not only scientific. These objects show us that complexity is ancient. The universe did not wait billions of years to begin building strange things. Very early, gravity gathered matter, gas cooled, stars ignited, black holes fed, dust formed, light escaped, was stretched by expansion, and eventually became the infrared glow that Webb now receives. The little red dots are reminders that the roots of today's galaxies, today's black holes, and perhaps even the conditions that eventually made planets possible reach far back into cosmic dawn. As we close tonight's journey, imagine one little red dot in a Webb deep field. It is so small that without the labels and analysis, you might pass over it completely. But inside that dot may be a young galaxy, a buried black hole, dense gas, ancient stars, and a story more than 13 billion years old. Its light began traveling before the sun existed, before Earth existed, before there were oceans, mountains, or living things here to receive it. It traveled through expanding space until a species on a small planet built a telescope delicate enough to catch it. That is the quiet wonder of astronomy. We cannot visit these places. We cannot touch the gas around Kuiper's LRD-Z9 or stand inside JADES-GS-z14-0. But we can receive their light. We can split that light into colors, measure its lines, and let it tell us what happened when the universe was young. Tonight, the little red dots do not need to be fully solved. It is enough to know they are there, glowing softly at the edge of time, inviting us to keep looking. So as you rest, let the scale become gentle, the early universe, once dark, beginning to fill with small islands of light. Webb drifting quietly in space, its mirror open like a golden flower, ancient photons arriving one by one, tiny red dots appearing in the data, not loud, not dramatic, but profound. And behind each one, a possibility, a first black hole, a first compact galaxy, a first hidden engine, a reminder that the universe began becoming mysterious almost as soon as it began becoming bright.